Medians and order statistics are essential concepts in analyzing data. The ith order statistic refers to the ith smallest element in a set of n elements. For example, the minimum of a set is the first order statistic, and the maximum is the nth order statistic. The median, commonly called the halfway point, divides the dataset into two halves. When n is odd, the median is located at position open parenthesis n plus 1 close parenthesis divided by 2. When n is even, there are two medians, the lower median at n divided by 2 and the upper median at open parenthesis n divided by 2 close parenthesis plus 1. For simplicity, we will refer to the lower median as the median. This chapter focuses on efficiently selecting the ith order statistic from a set of n distinct numbers. Although our discussion assumes distinct elements, the methods can often handle duplicates with minor adjustments. The selection problem is defined as identifying the element in the set that is greater than exactly a-1 other elements. While sorting this set and selecting the ith element is a simple approach, its time complexity of big O of n log n is not optimal. In this chapter, we will explore faster methods to solve this problem. The selection problem requires finding the ith order statistic in a dataset. A straightforward solution is to sort the data using algorithms like heap sort or merge sort, which requires big O of n log n time, and then retrieve the ith element. However, sorting all the elements is often unnecessary, especially when only one specific element is needed. We will introduce more efficient algorithms that solve the selection problem in linear time. These advanced techniques avoid the overhead of sorting by focusing on partitioning and recursive strategies. The goal is to identify the ith order statistic with minimal computational effort, making these methods more suitable for large datasets. This chapter is divided into 3 sections, each addressing different aspects of the selection problem. Section 9.1 examines the problem of finding the minimum and maximum elements in a dataset. Although basic, this step forms the foundation for more complex algorithms. Section 9.2 presents a randomized algorithm that achieves expected linear time, or big O of n, for the selection problem. This practical method assumes distinct elements for simplicity. Section 9.3 introduces a deterministic algorithm with a worst-case time complexity of big O of n. While this algorithm is theoretically significant, its practical applications are limited due to its complexity. These sections illustrate how different approaches balance theoretical guarantees and practical efficiency in solving the selection problem. Finding the minimum element in a dataset is a fundamental task. The minimum algorithm iterates through the array, updating the minimum whenever a smaller element is found. This requires n-1 comparisons, which is optimal for this problem. The necessity of n-1 comparisons can be understood through a tournament analogy. In this analogy, each comparison is treated as a match where the smaller element wins. To identify the overall minimum, every other element must lose at least once, requiring at least n-1 matches or comparisons. The minimum algorithm is optimal in this sense. Determining both the minimum and maximum elements simultaneously can be optimized beyond the naive approach of finding each independently. The naive method requires 2n-2 comparisons. However, by processing the elements in pairs, the number of comparisons can be reduced to 3 times the floor of n divided by 2. In this optimized approach, 2 elements are first compared to identify the smaller and larger. Then, the smaller is compared with the current minimum, and the larger with the current maximum. This process ensures that only 3 comparisons are needed for every 2 elements, significantly reducing the total number of comparisons. Whether n is odd or even, the total comparisons will not exceed 3 times the floor of n divided by 2. When tasked with finding both the minimum and maximum elements, processing the input in pairs offers an improved strategy over the naive approach. Instead of performing n-1 comparisons each for minimum and maximum, which totals 2n-2 comparisons, this method reduces the total comparisons to 3 times the floor of n divided by 2. Here's how it works. For each pair of elements, the smaller one is compared with the current minimum, and the larger one is compared with the current maximum. This approach ensures only 3 comparisons are needed for every 2 elements. For an even n, this strategy directly applies. For an odd n, an extra comparison is needed for the unpaired element, but the total number of comparisons still does not exceed 3 times the floor of n divided by 2. The improved algorithm for simultaneously finding the minimum and maximum processes elements in pairs. Each pair is first compared internally to identify the smaller and larger values. Then, the smaller is compared to the current minimum, and the larger to the current maximum. This strategy achieves an efficient 3 comparisons per pair of elements. This technique reduces the number of comparisons significantly. If n is even, the total number of comparisons is 3n divided by 2. If n is odd, there is an additional initial comparison for the unpaired element, but the total comparisons remain at most 3 times the floor of n divided by 2. This approach is particularly beneficial for applications requiring simultaneous minimum and maximum calculations. The general selection problem, which involves finding the ith order statistic, might seem more complex than finding just the minimum or maximum. However, an efficient randomized algorithm, called randomized select, achieves the same asymptotic running time of big theta of n. Randomized select is inspired by quicksort and recursively partitions the input array. Unlike quicksort, which processes both partitions, randomized select focuses only on the side containing the desired order statistic. This targeted approach avoids unnecessary computations and ensures an expected running time of big theta of n, assuming the input elements are distinct. The randomized select algorithm is modeled after quicksort but works on only one side of the partition. The algorithm first checks if the input array consists of a single element, in which case the answer is returned immediately. Otherwise, the array is partitioned, and the rank of the pivot element within the array is determined. If the pivot's rank matches the desired order statistic, the pivot is returned. Otherwise, the algorithm recursively processes either the lower or upper partition, depending on whether the desired order statistic is smaller or larger than the pivot's rank. This approach ensures efficient identification of the ith smallest element while avoiding unnecessary operations. The randomized select algorithm has a worst-case running time of big theta of n squared, similar to quicksort, but its expected running time is linear. The intuition behind this efficiency lies in the behavior of the pivot. If the pivot consistently falls within the middle half of the array, at least 1/4 of the remaining elements are ignored in subsequent recursive calls. On average, the expected number of partitionings is about double the ideal case, where the pivot always lands in the middle half. Since each partitioning involves fewer and fewer elements, the total work done across all recursive calls sums to big theta of n. This makes randomized select a practical and efficient solution to the selection problem. The randomized select algorithm is practical but does not guarantee linear time in the worst case. To address this limitation, a deterministic algorithm, select, ensures a worst-case time complexity of big theta of n. Like randomized select, select uses partitioning but guarantees a good split by carefully choosing the pivot. The key innovation of select is its method for finding the pivot. By recursively selecting the median of medians, the algorithm ensures that the pivot divides the array into reasonably balanced partitions. This guarantees that the recursive calls process progressively smaller subarrays, resulting in linear time even in the worst case. The select algorithm begins by dividing the array into groups of 5 elements. Each group is sorted, and the median of each group is identified. The medians are then collected into a smaller array, and the median of these medians is selected as the pivot. This pivot guarantees a balanced partitioning because at least 3/5 of the elements are either greater than or less than the pivot. The array is then partitioned around the pivot, and the algorithm recursively processes the relevant partition to find the ith order statistic. This systematic approach ensures the algorithm remains efficient, even in the worst-case scenario. The worst-case running time of the select algorithm is linear. The total work outside the recursive calls, including sorting the groups and partitioning the array, takes big theta of n time. The recursive call to find the median of medians processes a subarray of size n divided by 5, while the subsequent recursive call processes a subarray of size at most 7/10 of n. The recurrence for the running time is t of n equals t of n divided by 5 plus t of 7n divided by 10 plus big theta of n. Solving this recurrence shows that t of n equals big O of n, confirming the linear time complexity of select. Comparing select to sorting-based selection methods highlights the efficiency of linear time selection algorithms. Sorting-based approaches, which sort the entire array and then index the desired element, require big omega of n log n time in the comparison model. In contrast, both randomized select and select avoid sorting all elements. By focusing only on the relevant partition, these algorithms achieve linear time for the selection problem. While select guarantees worst-case linear time, randomized select is often preferred in practice due to its simplicity and efficiency for average cases. The key takeaways from the discussion on selection algorithms are as follows. First, both randomized and deterministic approaches can solve the selection problem in linear time. Unlike linear time sorting algorithms, these methods make no assumptions about the input's type, working effectively for any dataset where elements are distinct and pairwise comparable. Additionally, selection algorithms bypass the lower bound of big omega of n log n for sorting in the comparison model. While select offers theoretical guarantees, randomized select is often more practical due to its straightforward implementation and excellent performance in typical scenarios. In conclusion, the study of selection algorithms reveals efficient strategies for identifying order statistics, particularly the kth smallest element in a dataset. From the simplicity of randomized approaches like randomized select to the theoretical rigor of deterministic methods like select, these algorithms illustrate the power of divide and conquer techniques. The ability to achieve linear time for selection not only improves computational efficiency but also has practical implications in applications ranging from database queries to statistical analysis. By leveraging these advanced algorithms, we can solve the selection problem efficiently in both theory and practice.